Today we're going to do a fun problem in integrating rational functions that incorporates a lot of what we've talked about this week so far as integrating rational functions goes. One of the things that we want to notice is all the stuff that we've learned about polynomials in our adventures in integrating rational functions. We've noticed that there are only three integrals that we need: degree 0 over degree 1, degree 1 over degree 2, and degree 0 over degree 2. Those are the only integrating, as far as integrating rational functions goes, those are the ones that we need. The reason is all polynomials with real coefficients are going to have factors that are either degree 1 or degree 2. Any real zeros will correspond to degree 1 factors. Any complex zeros must come in conjugate pairs because we have real coefficients. And those complex conjugate pairs will come from a quadratic factor. So since we have partial fraction decomposition technology, we can break down any rational function so that the denominators of the terms are most degree 1 or 2. With some special carve-outs for powers of linear functions and powers of quadratic functions. But at their core, all we need are linears and quadratics for polynomials with real coefficients. So let's take a look at the things that we notice on this polynomial, on this rational function. What is the first thing that we notice about this rational function? What jumps out at you for this rational function? Besides the fact that there are a lot of terms. It's not about the amount of terms. What is it about these terms that draws your attention? What tells you something that you're going to have to do? Yeah. Correct. Correct. The degree of the numerator is greater than the degree of the denominator. When we talk about the degree of a polynomial, we only care about the leading term. So it's degree 4 over degree 3. That tells us that we're going to have to do long division. Good. So 1. It's degree 4 over degree 3, which means we're going to have to do long division. What else do we notice about this? What's another thing that we notice? With the light blue pen pointing at the denominator. The other thing we want to notice is that the degree of the denominator is 3. That means the denominator has a real 0. So the denominator has a real 0. What does that mean is in our future? Since the denominator has a real 0, we know that because it's cubic, we're going to have to write this as a linear factor and a quadratic factor, or 3 linear factors. So the denominator has a real 0. The denominator has a real 0 because it's odd degree. Therefore, we're going to have to do some partial fraction decomposition. And also, we're going to have to factor this denominator. So eventually we're also going to have to factor the denominator. The other algebraic trick has not shown up yet because we're not looking at anything quadratic yet. Any questions on our thinking before we start? Great. So I guess we got to start with our long division. Let's take our improper fraction and write it as a mixed number. We're going to break off a polynomial. It looks like our polynomial is going to lead with is going to be an x. Then we'll have a constant. And then we'll have a something squared over x cubed. Question? The partial fraction decomposition only works when the degree of the numerator is less than that of the denominator. Technically, we can do it at any time, but for our purposes, we only want to start partial fraction decomposition when the degree of the numerator is less than that of the denominator, because eventually that has to happen. If we do the partial fraction decomposition first, we're going to have to do long division in a bunch of terms. Let's take care of the long division now, and then do the partial fraction decomposition on the smaller terms. So great question, because there's not really an order of operation for this, right? In PEMDAS, there's no long division and partial fraction decomposition. Although long division is division, and partial fraction decomposition is breaking things into a sum. So maybe it's kind of. But PEMDAS is trash anyway. Don't do PEMDAS. Just learn to read. All right. So we're going to start with our long division, because one of the things that we want is the degree of the numerator to be less than that of the denominator. So x cubed minus x squared minus x minus 15 gets divided into 2x to the fourth minus 6x to the third plus 10x squared minus 16x plus 98. Now I'm going to double check that I copied that right. All right. So the first thing we ask, now when we're doing polynomial long division, we have a little bit of advantage over long division with numbers. With long division with numbers, I have to know the factors of this whole thing. With polynomial long division, I'm trying to subtract an x cubed from an x to the fourth. I don't have to worry about any of the other terms. I just have to subtract the x cubed from the x to the fourth. Secretly, we're doing that when we're doing long division. Because when we did 3 into 74 or whatever I picked, we're subtracting the 3 from the 70s. We're not worried about any of the other ones. So that shows up here by us only having to look at these first terms. So I need to subtract x to the third from 2x to the fourth. I need to do that x times. So I need a 2 times x. What we're trying to make happen is multiplying so that this 2x to the fourth, these will cancel out. But I have to multiply. I have to subtract 2x times this whole thing. I'm going to subtract x cubed minus x squared minus x minus 15 from this. Is it minus 15? From this fourth degree polynomial, 2x times. So I multiply everything by 2x. Minus 2x to the third, minus 2x squared, minus 30x. The first two terms cancel out, or the first term cancels out. That's by design. If that didn't happen, then something has gone wrong. Then we have to remember we're subtracting. -6 minus a -2 is -6 plus 2. So that's negative 4, x to the third. 10 minus a negative 2 is 10 plus 2, or 12, x squared. Negative 16 minus negative 30 is negative 16 plus 30. So is that 14? 98 minus 0 is 98. Bear with me through the first step. Long division is all about subtracting. How many times can I subtract x cubed from 2x to the fourth? I can do that 2x times. Now I need to think, how many times can I subtract x cubed from negative 4x cubed? And I can do that negative 4 times. Negative 4 times x cubed is negative 4x cubed. Negative 4 times negative x squared is positive 4x squared. Negative 4 times negative x plus 4x. Negative 4 times negative 15 is plus 60. Oh, 12x squared, thank you. Okay, that won't, there you go. Did I do the rest of them right? Thank you. The important thing to remember here is that we are subtracting, because it's a long division. Long division is about just repeated subtraction. The first thing that has to happen is these cancel out. This is both comforting and dangerous. You want to make sure that you got the right coefficients, that it actually subtracts to 0. You don't just want to install it. All right, and then 12 minus 4, we're going to have 8x squared. 14 minus 4 is 10x. 98 minus 60 is 38. Now, if I want to subtract x cubed from x squared, I'm going to need x's in the denominator, and that's what we're trying to avoid. That's for chapter 9, when we start talking about power series. So we're going to say now we can't subtract x cubed from x squared. This is our remainder. So our integral is the integral of 2x minus 4 plus 8x squared plus 10x plus 38 over x cubed minus x squared minus x minus 15. We've done the long division part. So we've broken out that polynomial 2x minus 4. Integrating that part is going to be no trouble. That's just an x squared minus 4x, and then here's the fraction part. From a standards and practices, we're going to put the plus c at the end of all this fraction business, but that plus c should really go between the 4x and the fraction part. If you really want to write down your answers with style, that's where you'll put it. You'll have x squared minus 4x plus c, then the fractions. And it's important not to explain yourself. And people are like, well, why'd you write the plus c in the middle? Like, well, if you get it, then you get it. It's what style. You just put the plus c at the end. That's more regular. People are going to find it there. So that's probably the better place to put it. But if you don't want to be like those Brittany and Justin wannabes, put it in the middle. Count down the degrees. Degree 1, degree 0, or sorry, degree 1. Sorry, this is going to be degree 2. Degree 1, degree 0, that's the plus c. degree -1, degree -2, degree -3. Have some style. But the problem that we're faced with now is our partial fraction decomposition. We've done the long division. The degree of the numerator is now less than that of the denominator. We're ready for partial fraction decomposition, which means we got to factor this polynomial. Now, we could grab a machine and factor the polynomial with the machine. If we're going to factor the polynomial with the machine, just in pursuance of partial fraction decomposition, stop. Go back to the original, plug that into the machine, and ask the machine to integrate it. If you're going to use a machine, use the machine. You know what I mean? So we're going to have to pull out some more polynomial knowledge. We'll notice that this cubic polynomial is not factorable by grouping. I can't just split it in half. Because the first two coefficients aren't multiples of the second two coefficients. Darn. Fortunately, we have some tools at our disposal. So notice that the polynomial ends in a 15 and opens with a 1. If this polynomial has a rational 0, it can be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Those are our only choices. The only possible zeros, plus or minus 1, 3, 5, and 15. I couldn't have a factor of 2 because it ends in 15. I'm not going to have no 7.5 running around. I have integer coefficients I'm trying to factor. If I have rational zeros, I'm going to have 1, 3, 5, or 15. They're going to be factors of this 15. I've shortened the list because the leading coefficient is 1. The leading coefficient was 2. 1 over 2, 1 over 1, 3 over 1, 5 over 1, 15 over 1, 1 over 2, 3 over 2, 5 over 2, 15 over 2. But the important thing is we have a short list of possible rational zeros. That 15 and the 1 give us this list of possible rational zeros. This is from the rational zero theorem. Might also find it as the rational roots theorem, because we used to call zeros roots. But then we're like, oh, we call roots roots. Maybe that's going to be confusing. So we started calling them zeros. Like I was there when this decision was made. I don't go to meetings. Now, at this point, you're thinking, man, that's a lot of zeros to check. So we're also going to notice something else. Now I remember why I picked this one. Notice that we start off, the first term is positive, the second term is negative, and then it's negative for the rest of the polynomial. This polynomial has one change in sign. So there's only one possible positive real zero. There's only one change in sign in the polynomial. So Descartes' rule of signs says that there's at most one positive real zero. Or sorry, there is one positive real zero. The number of positive real zeros of a polynomial is the number of changes in sign, or is less than that by an even number. So if I had 3 changes in sign, I could have 3 or 1 positive real zero. If we look at q of negative x, It will be negative x cubed minus x squared. Plus x minus 15. Descartes' rule of signs further states that if you look at q of negative x, you can also count the changes in sign. Q of negative x has 2 changes in sign. So there are 2 or 0 negative real zeros. There are 2 changes in sign, so there are 2 or 0 negative real zeros. This doesn't help us all that much, the negative real zeros. But this one positive real zero, that makes me want to focus on the positives. I'm not going to worry about -1, 3, 5, -5, and -15. I'm going to start with the positives because I know I have one positive real zero. My hope is that it's rational. And if it's rational, it'll be a 1, 3, 5, or 15. So this one positive real zero says, I want to start with the positives. Once we find that one positive real zero, we will be looking at a quadratic. We'll divide it out. We'll be looking at a quadratic. And then the quadratic, we won't have to do anything fancy to figure out. We'll just be able to look at the quadratic, decide if it's if it has real zeros or complex zeros. Any questions? All right. Yes.
So I'm just thinking for like you like negative x. Unitary signs. I mean, I understand.
Because the negative x gets squared and that becomes positive x. So we're still subtracting. There's 3 negatives: the negative from the x squared, and then 2 negatives in the square. So we're going to start by checking the positives. A fun tool for this is synthetic division. We have this as an option because we're just checking, we're dividing by a linear factor. So we're going to use synthetic division. Everybody remember synthetic division? So here's what what's going to happen. I'm going to check +1. I saw someone draw the box this way. It was pretty cool. Make sure there's 2 lines. There's a top line where the 1 is. There's another line. Then there's another space to write stuff. And then up here, I'm going to put 1, -1, -1, -15. Here's how synthetic division works. You drop the first one, the first one down. Oh, first of all, notice that these numbers up here, 1, -1, -1, 15, those are the coefficients of my polynomial. So when a number shows up down here, we multiply it by the number we're checking. 1 times 1 is 1. And then we add. -1 plus 1 is 0. 1 times 0 is 0. -1 and 0 is -1. 1 times -1 is -1. -15 minus 1 is -16. This is just a multiply add game. As soon as something shows up down here, we multiply it by 1 and put it on the next in the next column above one line. Then we add. Multiply, add. Does everybody remember synthetic division now? This is a super niche thing to know how to do. So we got to interpret what all this stuff means. What that means is that x cubed minus x squared minus x minus 15 divided by x minus 1 will give us x squared minus x minus 16 over x minus 1. Dang it. I knew I needed this space. So what this means for us is that x cubed minus x, x squared minus x minus 15 divided by x minus 1 is going to be x squared 0x minus 1 minus 16 over x minus 1. This is not what we wanted. I'm looking for a factor of x cubed minus x squared minus x minus 15. When we divide that by x minus 1, we get a remainder that's not 0. So that x minus 1 is not a factor of this polynomial. So synthetic division, if you're unfamiliar, is a way of dividing a polynomial by a linear factor. Moreover, a monic linear factor. If this was like 2x plus 1, I'd have to change it to a minus 1/2. So more importantly, 1 is not a factor. Sorry, 1 is not a 0 of this polynomial. So I'll move on to the next positive 0, which is a 3. So x cubed minus x squared minus x minus 15. Bring the 1 down. Anything under the line, we multiply. 3 times 1 is 3. 3 minus 1 is 2. 3 times 2 is 6. 6 minus 1 is 5. 3 times 5 is 15. 15 minus 15 is 0. And we have found it. So what that means is that x cubed minus x squared minus x minus 15 divided by x minus 3 is going to be x squared plus 2x plus 5. So those are our two factors of the x cubed minus x squared minus x minus 15. Synthetic division is for dividing by monic linear polynomials. Monic, because the leading coefficient is 1. Linear, because the degree is 1. Under certain conditions, it can be adapted for other polynomials, but let's reserve it for now for monic linear polynomials. We could also just take the 3 and plug it into the polynomial. But this, I think, might be faster still unless we use a machine. But if we're going to use a machine to evaluate the friggin' polynomial, just use that same machine to do the integration for you. We're not here to come up with answers. We're here for enlightenment. So we have further refined our integral. There's going to be a 2x minus 4. And now I've got the factors . Now notice, once I had that factor of x minus 3, I saw that the other factor was x squared plus 2x plus 5. That has complex zeros. We also notice that it has complex zeros and an x term. So eventually this is going to have to be, the square is going to have to be completed here. So that's how we're going to be reading that x squared plus 2x plus 5. That's not important right now. What we need to do is partial fraction decomposition on this fraction. So I'm just going to grab the fraction part. Partial fraction decomposition says rewrites our rational function as a sum of rational functions whose denominators are factors of our original rational function. Now we're going to just write the most generic generic numerators. Degree 0 goes over degree 1, and degree 1 over degree 2. If we're doing partial fraction, you can do partial fraction decomposition with cubic factors. I don't know why you would do this, but you can. On top, you would put a generic quadratic. But for our purposes, we can stop at the quadratics. Now all we have to do is figure out A, B, and C. And we're going to get there by adding these fractions and equating the coefficients. So I'll have A times x squared plus 2x plus 5 plus bx plus c times x minus 3. Let's see what we have. Let's see, I'll start multiplying this out. We have ax squared let's see, we're also going to have an x squared here plus bx times x. That's going to give us a plus bx squared. Any other x squared terms going to show up? I know I just jumped from one distributive property to the other. But what I'm doing is I'm looking for x squared terms. Now let's go after any x terms that might be there. So I'm going to have 2a times x and over here I'll have minus 3bx plus cx. Those are all of my x terms. Because remember, I'm going to be equating coefficients. I need to know what's in front of x squared, what's in front of x, what's constant. And then finally, I'll go grab my constant terms, which is going to be 5a and 3c. So my x squared terms, I've got ax squared and bx squared, so a plus b times the x squared. My linear terms are 2ax minus 3bx plus cx. So I've got 2a minus 3b plus c times x. And my constant term is 5a minus 3c. Oh, whoops. Now we have a system of 3 equations with 3 unknowns, a, b, and c to solve. A plus b is equal to 8. Two a minus 3b plus c is equal to 10. And 5a minus 3c is equal to 38. Now we could grab a machine and ask it to solve this system of equations, but if we're going to use a machine to solve the system of equations, then we might as well just use the machine to integrate the function. Both fortunately for our heroes and unfortunately for our heroes, we're out of time for today. So I need you to solve this system so you can continue integrating this function. We'll go over the answer on Monday if I remember to do so. That's going to do it for today. That's going to do it for this week. I'll see you all on Monday. So have a good weekend. Thanks for playing. Thank you, Professor. Have a good weekend.
What do you think the X plus C mean? For the.
Oh, so we have to write bx plus c because the denominator is quadratic with complex zeros. So we always write the numerator as big as it could possibly be. And that's degree 1, because it has to be less than that of the denominator.
And the plus C numeric has, well, like the same reason.
No, the plus c is there because I'm writing a generic linear. A linear is not just an x term, it's an x term plus a constant term. We have to get all the terms that are degree less than 2.
I thought that like X by itself is, I mean, I can see why that would work here, because you would have, like, I thought that X by itself is, or,
It is a linear term, but we need the most general linear term.
oh, let's see.
So we might have a constant term.